Let's see. Okay. I think we're good to go. Does everybody see us now in the chat? I think we're good to go. Let's see. Okay, perfect. All right. So I guess I could just do a quick little introduction again, too. We kind of had a little test run. So sorry about that. Some technical difficulties. Obviously, with our luck, the last session of the day, that's the one where things start to kind of go a little awry. But again, guys, thank you for joining us for the last session of the day. We're here with Max Rohr. Again, like all the other sessions, please feel free to send your questions into the chat that you see on the right-hand side. All right. Also, Max does have a poll that's currently going up. So please send in your feedback for the poll so we can kind of get a gauge for the conversation that we're about to have. But again, I will quickly introduce Max as well, too. So after graduating from the University of Utah, Max began his manufacturing career at the Caleffi headquarters in Italy. He had 20 years of work experience in installation, distribution, manufacturer's representative, and manufacturing roles before returning to Caleffi in 2020. And Max also describes himself as an energy nerd. So Max, the floor is yours. Again, sorry, guys, for that little technical delay, but we're here and we're ready to roll. So Max, take it away.
Yeah, thank you. Thank you for having me today, and thanks for sticking around to the last presentation of the day. What we're going to talk about today with this session is primary, secondary piping, but beyond kind of the basics of what it is into when would you use version A, B, or C? And I'll cover those different topics as we go through. So I'm interested to hear which one you prefer before we even get into the topic. So feel free on the right there, kind of near the chat, if you want to type or select an answer for the poll. And then if you have something you want to ask me as we go through, feel free to type that in, and we can ask those as we go. So to start with, here are the learning objectives. We're going to talk about defining primary, secondary piping, why we should use it, why it's important, when to use it, and when you may not need to use it. We'll talk about the importance of that as it relates to the other components, and then cover some reasons to use different types of hydro separator technology and things like that. Then we'll wrap up with air, dirt, and magnetic separation. So if you're looking for additional Caleffi resources, here's a QR code that goes right to our Hydronics registration page. I won't spend a ton of time here, but let us know how we can help with any other training things that you have in the future. Also, keep coming to these sessions. It sounds like this is going to be a series throughout the year, which is great. So if you need BIM files or master spec help, we've got those up on the website, and I'll kind of move on to today's topic. So let's start with what is primary, secondary piping. So I've got a machine here that I've built. I'd like to run this by you. We've got a good sample size here to let me know if you have any notes about this machine that I built. Does anybody see a problem with this machine? Feel free to type something in the poll there if you've got any suggestions for how I could improve this design. I'll hit play on that one more time. So we've got two gears that are spinning at very different speeds that are in contact with each other. So we have a potential to, as I can see in the chat, it's broken. It's a good way to put that. We're going to strip a gear here. We're going to bind up the gears. This machine is not something, as a manufacturer, I would put a 10-year warranty on or a one-day warranty. We've got a problem here. We need to fix this machine. So we would probably all agree that this machine is not long for this world. What if we put it into the context of, instead of rotations per minute, gallons per minute? So now let's say that we've got a boiler circulator spinning at 10 GPM, and we have the system side. We've got all of these, we'll say they're single speed pumps on at the same time. All the zones are calling. We've got a very different amount of GPM on the right side of this system than the left side. This is a problem. This is broken in the same way that was mentioned. The machine is still broken. It just is broken in a GPM sense instead of a rotation per minute sense in a simple machine with just two gears in it. So this is the essential problem that we have to solve. Inside of this box right here, we have to do something to keep these two gears from fighting, to keep these gears from grinding. What that means in a hydronic system is that we're going to, if we have gears in conflict like this spinning at different speeds, we're going to influence flow on one side of the equation or the other. So we may be pushing way more flow than we need through the boiler heat exchanger, or we may be way less than we need in some scenarios. And we don't want that. We don't want these two different things to fight each other. We've got to put in some sort of device in the center. So broadly speaking, what we're talking about is primary secondary piping. So let me talk a little bit about if we didn't do any of this, if we just connected those two pipes straight across. In that last slide, we don't address anything. In this scenario, and this is pretty common down in the States, I think that you guys in Canada do a better job of paying attention to some of the new technologies and things that need to change with the heat emitter options and energy source options, like new modulating condensing boilers and heat pumps and things like that. There are a lot of places in the States where the least expensive way to replace a cast iron boiler that may have failed is to just put in a mod con and not change anything else. Just put a couple unions in there to make it easy for yourself, but then you're off and running. There's a problem here. We now have 4 different circulators that could come on and off. This heat exchanger in a mod con is going to be more picky about the flow rate that it wants. That's why a lot of the modulating condensing boilers just ship either with a circulator in the cabinet mounted already or in the box ready to plug in, because we don't want to leave this up to chance. We don't want to have some wide range of flow rates that could be 5 GPM or could be 20 GPM. We want to make sure that we've got a very specific flow rate through that boiler. This isn't a big 20-gallon cast iron boiler with a lot of buffer capacity and a lot of volume that we can just kind of send a huge range of flow rates through. It's going to short cycle. It's going to have a hard time if we're below the minimum flow rate. It's going to go to post purge and come back on. It's not going to work very well. So what do we do instead? So simply speaking, what we're doing with primary secondary piping is we're just separating these two wheels. So this machine, as Hart mentioned, is now, we've unbroken it. This is a functioning machine again because these gears aren't touching each other. So these gears can spin at different speeds and they're not grinding. They're not creating an issue where they would bind up or we're influencing flow on one side or the other. So that's kind of the essential piece of primary secondary piping. There are a lot of different analogies to this. We're going to have a follow-up article that's going to run in the CMPX issue that's going to talk about this with a few more examples as well, if you need something that's kind of written to refer to. But that's what we're doing with primary secondary piping. There are 3 different ways that I'm going to describe that we can do this. This is a low loss header or a hydraulic separator. There are a bunch of different names for this device, but that's really all that we're doing is moving those 2 wheels so they're no longer touching each other. And I'll go through the different flow examples of what can happen inside of these devices as we move on. There are a lot of different separators on the market. I've got a slide a little bit later that shows some more examples, but really there's not a lot going on in here from the hydro separator perspective. It's just a big open vessel. It may have a collision media, which I'll cover later. It may just be an open tank, but that's really all that is happening here. There's not some sort of diversion that's happening with a motorized actuator or anything complicated like that. It's not mixing for a specific temperature. It's just a big wide spot in the river where those 2 flow rates can kind of bypass each other. So let's say that we are going to put in a hydro separator and somebody says, well, you don't need one of those. Does anybody have an example of where that could be true, that you wouldn't need primary, secondary piping at all, not any of the diversions, buffer tank, closely spaced tees, or a low loss header? If anybody has an example of where you could be right that we don't need to have 2 different circulators or more, we just need kind of straight pipe from the boiler out to the system and back. So I'm going to give you one, and I'll wait for some answers in the chat if anybody has another one. Let's say we have a snowmelt boiler and just one enormous zone of snowmelt. So the conditions are the snowmelt is off or the snowmelt is on. It's a 0 or a 1 here. We don't have a bunch of different flow rates possible on this side, a bunch of different flow rates possible on this side. It's either on or it's off. So in that case, if you had 10 GPM on the boiler side and you had 10 GPM on the system side, you could have just a straight shot across the hydro separator and back. So in this, I see in the example or in the chat there, of one zone example is right. So in this example, I could put a little drop of food coloring right here, and it would just kind of float right there. It wouldn't go anywhere because we've just got kind of stagnant conditions right in the center as we're going straight across the top and straight across the bottom. So it would look like this. We've got two wheels spinning at the exact same speed. So in a one zone snow melt system, that could be a good way to go. You could save a little bit of money there as long as your circulator can overcome the pressure drop of both the PEX pipe going out into the snow melt and the boiler heat exchanger and all of the piping, the distribution piping in between. If your boiler circulator can take care of both of those, maybe you don't need a system circulator. So kind of a rare example, I would argue. Most systems are going to have multiple zones, or they're going to, that might put you into a situation where one circulator to take care of both sides could be a commercial circulator that would be more expensive than buying two more residential size circulators that just take care of each side of the equation independently. So even in a single zone snowmelt system, a primary secondary device wouldn't hurt anything. But it may be something that isn't required.
As you can see also, Max, too, in the chat, we kind of have some different comments as well, too. I guess people were kind of referring to your answer as well. We have one person that was talking about gravity conversion. Another person answered buffer tank. Another person answered air handle / boiler with close proximity. And then also one more person added both loops with the same flow rate.
Yep. So all of those are good examples. So those would be cases that we've got kind of an on-off condition. We could get away with no multiple different flow rates on the right side of the equation here. However, I would say most of the time, we're going to have some difference in a multi-zone system. Or let's say we have multiple boilers or something like that, where it's not just a single boiler that's on and off, but it's 4 boilers that are cascaded together. In that case, we could have, let's say, 10 GPM on the left side and then 5 GPM on the right side. Maybe the building is pretty well up to temperature. The sun came out. There's only one zone calling. We've got an ECM circulator, so that's slowed down on the right side. But the boiler needs to maintain a minimum flow rate to stay happy with whatever that single speed pump is. And a simple example, this is a case where inside of that hydro separator, we're gonna have 5 GPM just go right back to the boiler. So to keep that 10 GPM that we need for the boiler heat exchanger, 5 GPM are just going to peel right off and go back to the return of the boiler or the heat pump or whatever the case may be. So we're only really pulling off the 5 GPM that we need to keep this wheel spinning at the right speed. So that's kind of the simple magic of primary secondary piping, is if there is an imbalance, we just have enough space for that flow rate to go back through this big wide open vessel without a lot of pressure drop here, and it keeps the the customer on the left side of the equation happy. The opposite could be true. So let's say this is even kind of a tricky example. Let's say we have a 400,000 BTU per hour boiler, and we have a 400,000 BTU per hour load. Everything sized great, came out just like right on the numbers. Both are the exact same number. There is a scenario that the boiler is turning away at 100%. We have all of the zones are wide open. The circulator is moving at the maximum speed that we had planned for that scenario. It's a design day. We could still have these wheels spinning at different speeds. So this could be a 20-degree delta T across the boiler heat exchanger, and this could be a 5-degree delta T across some fan coils or something like that. So even in a scenario where we're moving the same amount of BTUs out to the system, this could be spinning faster. And that's one of the things that's a little tricky about primary secondary piping, is the same flow rate on both sides. Also, you're anticipating the same delta T, which is potentially possible, but probably not going to be the case most of the time. You might have a difference there. And that's what primary secondary, again, just kind of quietly solves that problem. Okay, let's talk about the first way to do primary secondary piping. So looking at the poll, it looks like we had the answers for what's your go-to method before I get into the 3 different versions between a buffer tank, closely spaced tees, and hydro separators. We had 33% say buffer tank, 66% say hydro separators, and 0 say closely spaced tees. I think this is because we're doing this presentation in Canada. If we do this in the States, everybody's like, oh, you can save a lot of money with closely spaced tees. And I would argue that's not necessarily the case, but I'll get into that in a few slides here. So closely spaced tees is kind of the time-tested least expensive purchase price to do primary secondary correctly. It absolutely will work. I've got some nuances on the next slide for things to be careful with, but closely spaced tees will absolutely do the job. If you've got a closely spaced setup here, where inside, if you could measure it with a little flow meter right in the center there, if that's moving at less than 2 to 4 feet per second velocity, you're in good shape. You've got a scenario where this gear can spin at a different speed from this gear over here. It's going to work for you. Here are the like comma but portion of that answer. This is really critical. If we say closely spaced tees, the book answer is no more than 4 pipe diameters apart. So in a lot of boiler manuals for years, it would say things like maximum of 12 inches. And that's a good answer if you've got 3-inch pipe. That's a bad answer if you've got 1-inch pipe. So we don't want 1-inch pipe to be 12 inches apart. That's not closely spaced anymore. So there's going to be more of a pressure drop here, and the path of least resistance may be, instead of separating that gear where the GPM come back here, if it's in excess of what we need on the system side, some of that peels off and it starts to push the circulators downstream out into the system side. We've broken that scenario, and we've started to bring the gears back into conflict a little bit. So yes, you have a question?
So we have a question here in the chat, so I'll read it from there. So can the low loss header not let VSC know where to set flow for its side of the loops?
Can it let
to set flow for its side of the loops?
It doesn't have any control. So that would be a circulator selection or some sort of other valving option with a balancing valve or something. The inside of the hydro separator doesn't have any ability to influence flow. It's just going to allow whatever happens, and the one side bypass to the other, if I'm understanding that question correctly. So that's not what that device would do. You could use some sort of 3-way mixing valve or something like that to actually divert for a specific temperature and mechanically change the flow path there, but that's not really what the hydro separator does. Another thing that's critical with the primary secondary piping is that you need these straight lengths upstream and downstream, so this isn't too turbulent right in the heart of the primary secondary device here, which is closely spaced tees in this example. This one I see broken all the time as well. So out in the field, you'll see a 90-degree turn coming right into the closely spaced tees, or on the outlet where we don't have the minimum pipe diameters. Again, we're starting to create a little bit more pressure drop potential here, and we could affect that best case scenario where we've completely separated the wheels. So if you see primary secondary with closely spaced tees out in the field that looks like this, you're in pretty good shape. If you don't see it quite following all these rules, that would be a pretty typical thing to find out in the field, unfortunately. So can be done, just like anything in the world, just you have to pay attention to the details, and these are a couple things that set you up to actually do closely spaced tees correctly. So this is not to scale or anything, but just to show that, and I think I even have my colors backwards here, but just to show that closely spaced tees following the rules for being closely spaced, this might be just out of tolerance in this photo here. And then additionally, we need a lot of real estate on the wall here to make this work if we're talking about 1.5-inch pipe or something like that. So closely spaced tees, when you pick them up at the wholesale house, they're 2 tees that they can fit in your hand. To do it right on the wall, you need to plan for that. That's going to take up a decent amount of space, and you might really have to think about how you can get that into a small mechanical room without breaking the rules and having a quick 90 off of that or something like that. Okay, option number 2. Let's say that we are going to go with a buffer tank. There are a bunch of different reasons that we might be using a buffer tank. One would be, let's say we're replacing a modulating condensing boiler with a heat pump. The heat pump manufacturer may say, you need to have a buffer tank. We can't cycle this compressor 10 times in an hour. That wouldn't be good for a mod con either, but it just is going to void the warranty of the heat pump to not have a buffer tank. I think that is the case with some of the technologies that are on the market right now. So we need to make sure that we're setting up the new equipment for a long service life. We want to make sure that we've got some buffer capacity so it can have a 30-minute run cycle or whatever we design there. So a buffer tank is just a supersized hydro separator. This is just a big open vessel here that's going to give us a big thermal battery to charge up. And then it's such a big wide open lake of water in here that the pressure drop is minimal for the supply to come back to the return here. So it still works well to be a primary secondary device. It's just the biggest, most expensive version because it's a pressure vessel that's going to be insulated versus two copper tees that you could pick up at a wholesale counter or something like that. So this is something that provides some additional benefits. There's a formula that we've got in Hydronics 17 that can go into a little bit more detail for, well, what size buffer tank are we talking about here? And these are the different variables that we have to know to size the minimum buffer tank for what we're looking to do. So if we say that we have a 50,000 BTU boiler that can turn down to 10,000 BTU, so it's got a 5-to-1 turn down ratio, we would like that equipment to be on for a minimum of 20 minutes each time that it fires. So that would be great for the cycle efficiency of the system and to make sure that the energy efficiency of every BTU of gas or every unit of electricity that we're using is put to good use and not in a gas scenario just going up and out the flue every time we go to a post-purge, pre-purge cycle. And then we need to know something about the system. We need to know what is the smallest load. Is there like a single towel warmer radiator in a guest bathroom or something like that? What is the minimum load that could be on that would be enough to cool down the buffer tank and fire the boiler? And then we need to know how cold can we let this buffer tank go? Can we charge this up to 180 degrees in the morning and let it fall all the way down to 105 degrees throughout the day? Probably not. We probably want to shoot for something like 140 degrees that can fall to 120 degrees. So we still have some usable energy in there. That might be a good example. So in that case, we'll have a 20-degree delta T. So all of this sizes out to a 17-gallon buffer tank. With a modulating boiler, it's going to be smaller than you would think. If this were a single-speed boiler or high-low boiler of an older technology, then you would need more buffer capacity because you can't slow down the boiler as much. So this is just to show that you could have a 17-gallon buffer tank that would almost look like a big hydro separator, and that would work in this case. How do we pipe these things? The traditional one is like a hydro separator, that we've got 4 ports, just like you would do for a boiler that we showed in an earlier slide, that we've got the supply across the top going out to the system and back. Here are some things that can get a little tricky with the buffer tank. So let's say the delta T on the heat pump side is 20 degrees, and on the load side, it's 5 degrees. For whatever reason, we've got kind of a big difference there. In that case, we're going to have this pump moving a lot faster on the right side, and it's going to churn up the stratification of our tank. So that's a little bit of a problem because ideally we stratify this buffer tank so the hottest water is at the top. We don't have to recycle it as frequently. If we're moving really fast through this tank, we're going to churn it up. So instead of being 140 at the top and 130 at the bottom, it's just a uniform temperature all the way throughout. And that could be kind of a problem because we like to stratify that tank and use the warmest energy for the longest amount of time so we don't have to fire the boiler. So that can work. I would say 4-port, 4-pipe tank configurations are a good fit if you have a reasonable delta T on both sides that's within 5 degrees or something like that. That might be a better way to go. So what are some other options for how we pipe these tanks? So we could cap plug the right side of the buffer tank here or by a 2-pipe configuration. And in this scenario, if we turn on the heat pump and the power went out for 8 hours or something like that, so it's a design day, this ECM circulator is moving at 100% of whatever the flow rate is. In that case, the heat pump kicks on, all of that water goes right out to the building, and it comes back, and it goes right into the return of the heat pump or the boiler. In that scenario, this is just a stagnant tub of water. Nothing's happening there. As this ECM circulator starts to slow down, some of the zones close, then we start to have some energy going out to the building direct to load still, but some of it's going to come back into the buffer tank and start to charge this up. So we'll charge up this battery, and then the heat pump may even turn off. And if there's just a little bit of energy going out to the building still, we can actually pull from the right to the left out to the system here. And we're actually just using the battery to power the building until this thermal battery runs out of energy. So that's a 2-pipe configuration. That can be a really good fit if we've got a pretty wide range of flow rates and delta T's that are possible out into the system. So 3-pipe configuration is similar. We're just always bringing the return back through the full thermal mass of the tank. So we're going to have to charge that all the way up each time. Depends on the system, and we've got a little bit more detail on that Hydronics 17 as well. This is something that we didn't talk about for a little while because it was something that was part of a solar thermal time in our industry where solar thermal was really popular. And then modulating condensing boilers just got really good. The turndowns got really low. So people were saying, wow, we don't need buffer tanks anymore. And now it's kind of coming back, the pendulum swinging again, because heat pumps are saying, no, we want to have a buffer tank again. So we need to figure out how to size and pipe these things again. This is what a buffer tank looked like in the solar thermal days. When we were in that industry more before PV just kind of did a better job and got less expensive quicker. So this is just a 4-port buffer tank for a geo exchange solar combo system. Okay, the third choice is a hydro separator. So low loss header or hydro separator, those are synonyms for this device. So this is primary, secondary in a box essentially. There's no secret to how to build a hydro separator. The way to do it right is to have a 3-to-1 ratio between the barrel and the inlets. So if it's a 1-inch pipe connection, that barrel needs to be a minimum of 3 inches. If it's 6 inches, it's just a buffer tank at that point. It's just a very expensive hydro separator that has become a little buffer tank. So I'll go through sizing in a second to show you where that would line up. There are some of the things, just speaking a little critically of other devices that exist in the market. If you don't have a 3-to-1 ratio, you're not properly separated there. So you can take some cost out of these devices and make this a 2-inch or a 2.5-inch, or make it out of a different material that the inside diameter is not as big as it would be in a big steel vessel like this. And you're going to influence some flow at a different flow rate. So that's something to pay attention to. We've tested this with some other devices on the market where we put a flow meter right here. You could even just look at the screens on the circulators in some cases. If you have just a boiler circulator on and you see anything other than 0 GPM on this dot right here, you're not actually separated anymore. That's the test. So if you had a flow meter here and you see some flow when none of these circulators are on, you're influencing flow across that device, and it could be that it's undersized. It could be that it's the proper device. It's just as, you went with a 1-inch instead of a 2-inch or something like that. That could come up as well. Okay, I mentioned earlier that the closely spaced tees were the least expensive way to do primary, secondary piping, if you count labor. So unless somewhere up in Canada you have somebody that can solder up this entire system or press or whatever connection style you use for $5 Canadian an hour. I'm sure that's like well below the minimum wage anyway, but if you could find somebody that could put that together, or your niece or nephew could do that for you at that price, go for it. That would be a less expensive thing to do, even buying an air and dirt separator. I would say realistically, the labor to do 10 field connections with air, dirt, closely spaced tees, 10 minimum connections to get this together. And as we talked about with that proper spacing and things like that, maybe more expensive total installed cost to do closely spaced tees, factoring in the labor, compared to a hydro separator where you've got 4 union connections that you can use press or sweat or NPT and kind of keep moving. All of this has been pressure tested and tested for functionality by whatever factory you buy hydro separator from. So there's some peace of mind there that if something leaks, it's going to be a warranty item and not just like installer error. If you have a leak with your closely spaced tees, you're not going to get any money back from a brass company there. That's kind of on you if there's a leak in that system. So I would argue that factoring in the labor, that the hydro separator may seem like an expensive purchase price at the wholesale house, it's high potential that it would be less expensive to get it in and commissioned properly. So another thing to mention about hydro separators as far as what's going on inside of the device is there are kind of standard hydroseparators, and these are both right out of our catalog. We make both of these where there's either nothing on the inside or a simple baffle to help separate the air a little bit. I'll talk about these collision medias a little bit further along in the presentation. But this is a more cost competitive version. There's not a high performance collision media to separate the air and dirt very well in the system. Maybe you buy one of these and then also have a Y strainer and also have a big air separator somewhere else in the system. I've seen that sometimes where people will have like a big magnetic separator separate to this device. I would argue that it's easier to do this where you just have a high performance air separation media, coalescing media, and also the dirt and magnetic built into one device. That's what I would consider a high performance category. These aren't apples to apple comparisons. So that's something that we also talk to the engineers about when we're doing trainings, that, okay, hydroseparator doesn't mean hydroseparator in all cases. You want to look for something that has this collision media all the way across, or you're wasting a little bit of the potential of these devices, because the velocity going through a hydroseparator is slow. That's how it works to separate the gears. So it's a really great spot to separate air and dirt effectively, and this little media helps us do that. Okay, and this part adds magnetic as well. So how do we size these things? Pretty easy compared to something like a point of distribution mixing valve for a plumbing system, where we have to know a lot of variables and a lot of things about the building. For this, we have to know what the higher flow rate is on the energy source side, the boiler, heat pump, or chiller side, or on the system side. So let's say in this example, the primary loop, we'll say it's on the left side, is 140 GPM max flow rate, and the secondary is 230. So we've got a different delta T in that scenario. So we just pick the bigger number, just one of those numbers. We don't have to combine these or anything. We don't have to add them together. So in this case, to cover the biggest number there, we want a 247 is going to be a good fit. So a 4-inch separator. You could buy a 14-inch separator and you would make me, a Caleffi employee, very happy, because that's going to be a very expensive tank. Actually, don't do that, because we only go up to 12-inch CRN separators in Canada. So don't buy a 14-inch, or you're not going to have the right listing. So let's say you buy that. It's going to be a very expensive buffer tank. You could probably buy a buffer tank that would have a much bigger capacity for less money at that point. The 12-inch is only required if you need an 1850 GPM flow rate. So that's, the sizing is pretty straightforward there. You could go a size bigger if there wasn't a 4-inch in stock at a wholesale house and you needed one right away, and all they have is a 5-inch. That would be fine. You'd just be overpaying a little bit for that device, but it would work okay. So one of the next questions that we get is, where do we put the expansion tank? It's a little bit more straightforward with closely spaced tees. We want to, like Dan Holohan says, we want to pump away from the expansion tank. So my book answer would be, let's put the expansion tank right on the inlet of the boiler circulator. We're pumping away from that, and we're going out to the system from there. So this is a good spot. The expansion tank is on the coldest water on the return to the boiler. So that's good just for the longevity of the expansion tank. The rubber diaphragm, or bladder, whatever style that you're using, if that's on the hot side, even if it's on the inlet to the system circulator, the warmer temperature is something that can reduce the service life of that component. Maybe not drastically, but best case scenario, I'd put it on the coldest spot right before the boiler circulator. An interesting part of the hydroseparators is, because the pressure drop is so minimal for the hydraulic separation to work effectively, you could actually put the expansion tank right on the right side here, and it would effectively still be pumping away, because this is such a minimal pressure drop across this vessel. If this were a balancing valve or any other sort of control valve, you wouldn't want to do that. You'd want to get that expansion tank closer, but this would be okay. The one on the bottom of the separator that I discourage is for a couple different reasons. One, the makeup water is going to go through this vessel and push the debris potentially right back into the circulator and the boiler heat exchanger, which is exactly what we're trying to prevent. Same thing could happen as the system fluid expands and contracts. So as you fire up the system for the first time in the fall for a heating system, and the bladder it expands and contracts with the temperature of the water, you could just basically inject all of that dirt right back into the system, which is exactly what we're trying to avoid. So that would be a place that I would discourage, even though there is a nice tap there already. We see this quite a bit. Even if you put the expansion tank off to the side with a T or something, that would be a little bit better. But best case, we want to put it in one of these two locations, so we're not pushing that dirt that's been neatly separated to the bottom of the hydro separator anywhere, but staying right there until we have the opportunity to blow it down. Okay, here's a project example of a hydro separator. So what I would point out here is to get primary, secondary piping right with all the proper spacings, you can actually go right into a hydro separator with an elbow. There are no minimum distances here like with closely spaced tees. This is a pretty small amount of real estate for what might be 2-inch, 2.5-inch pipe with those two boilers combining. So that's a pretty big pipe. This, if it were closely spaced tees, might be wider than the shoulders of these two guys that did the installation that are having a good time showing off this cool job site. So that is a very small package to do primary, secondary correctly. That's one thing that can be really helpful in mechanical rooms that are getting smaller and smaller and smaller. I don't know if it's the case up in Canada, but I was a manufacturer's rep in Colorado for a while, and one of the tax law loopholes was that if you had a crawl space that was less than 5 feet and put the mechanical room in there, it didn't count as occupied space that you paid taxes on. So effectively what that meant in Colorado is people would jam all of this, the architects would jam all of this into a 4.5-foot crawl space, because then the owners didn't have to pay taxes on that space, which is just a crazy loophole. But in that case, it was very helpful to have a hydro separator just because there was less height needed to get it right, less space needed to put a hydro separator in there and have the proper performance of the system, even with limited vertical space. And that could just be an old building where you don't have a lot of vertical space anywhere. So I see Tasha said there are most mechanical rooms in modern Canadian buildings are a bigger size. That's good. Some of the old ones are really small, was the other note. Yeah, it's helpful if modern building codes give you enough space to do the mechanical system correctly. Feel free to write your friendly code officials in the States. I'd appreciate it. So you can use a hydro separator in chilled water applications too. This is actually a big ice rink in Texas that they use chilled water. It's just the hot water is on the other side. So that's kind of the difference, is that we flip hot and cold. Basically, it has to be really well insulated so it doesn't sweat all over the floor. Okay, now let's wrap up with some air, dirt, and magnetic separation kind of details as well. So air vents are going to be great at getting air that has gathered, just because of the natural buoyancy of air inside of a closed loop system, at the top of something. So an air vent is going to be great at the top of a riser, solar panel, or hydro separator, buffer tank, or something like that. The way that an air vent works, an automatic air vent with a float style, we have some that you would go into a radiator or something to just bleed a little bit of air out of the top of a radiator. The way that an automatic air vent works with a float is, as that air gathers at the top, it allows this float to drop. It opens this little needle valve and it allows air to come out. Then as the air escapes, the float comes back up. If you've ever seen an air vent in the field that leaked, what happened is something is holding this up. So it could be a little piece of Teflon tape, it could be a wood chip or a piece of plastic or something like that that is stuck there and it's allowing water to go through. One of the things that I used to do as a contractor is that to commission a system, I'd go to the air vent and I'd take my fingernail or a little like Techmar screwdriver or something like that, and I would push down this needle valve to get that little last gulp of air out. And then as soon as I felt a little bit of water, I would release it. The reason that you should not do that, that I know now, is we actually want this little buffer space of air there. So that's how the automatic air vent will work naturally, is it's going to leave the water level about an inch, or in a commercial application might be 4 inches below the needle valve, because we don't want that garbage that's accumulated at the top of the system that is like a wood chip or something that would float to get in contact with the needle valve. So we want that little space in between the needle valve and the line of the water level, so we don't have something get in contact there and get hung up, and that's what would cause an air vent to leak. Can be serviced. You can take that whole cap off, just take some compressed air through that and get the debris out in a lot of cases. Okay, so I mentioned this before. The coalescing media is a very fancy way of saying to gather. So a coalescing media, there are different manufacturers that are going to make different versions of this same kind of device, that you're going to have some sort of media here with sharp edges where we're going to have a little eddy with the flow of the water coming through, that it's going to get kind of hung up on a little knife edge around. In our case, it looks a little bit like a honeycomb, that it gets right into an eddy on that sharp edge, and then it gathers into bigger bubbles as more bubbles get hung up on that same edge, and then as they get bigger, they float up to the top, which is the same air vent that was described before. So coalescing media is helpful to get those little micro bubbles out. I'll talk about that in another slide. And then also helpful on the dirt separation side to have little pieces of debris fall down to the bottom. They collide and fall down, but they don't plug. I'll show an example versus a Y strainer, how a collision media is different there. So getting the air out of a system actually is three different types of air, three different categories of air that we need to get out. Something like a big air scoop like this is going to be good at getting out stationary air pockets. Like if you first turned on the water to a garden hose and you hear kind of big gulps of air coming out, something like this is going to be good at getting that big bubble of air out, bulk air. The harder ones are entrained air. So this is going to be micro bubbles that are going to look like if you poured water out of your kitchen faucet into a glass and it looks milky for a second, and then those entrained air bubbles kind of float out to the top because they're now at atmospheric pressure. That is a micro bubble that's going to be harder to catch. That's what we need this collision media for. Otherwise, it's just going to go straight through a device like this. The micro bubbles are going to go below these fins. They're carried by the velocity of the circulator. They're going to keep going and keep rusting other pieces of the system. So we don't want that. The last category is gases dissolved within the water, and that's actually related to expansion tank and circulator location in relation to the air separator. So you could have a great air separator just in the wrong spot, and you wouldn't get those gases dissolved in the water. So how we want to address that is to have the air separator on the hottest point of the system at the lowest pressure. So this is a chart that kind of shows where points A, B, C, and D line up. Point A is 170 degrees, so we've kind of cooked the water and we've cooked the air bubbles out of the water. They've come out of solution, and it's a low enough pressure that we can get that right out at the top of the air separator there. If we were to put that same air separator at position B, we've just boosted the pressure with the circulator up to 32 psi in this example. Even though the temperature's hot, we just forced all those bubbles back into solution. So you could have an air separator that was sized properly, that's a high performance air separator in position B, and not get all of the air out of the system because it's coming back out of solution at position C or position D, and maybe is continuing to rust the boiler heat exchanger or something. So that's the third piece of the equation there, relates to where you put that air separator, and that's the hottest, lowest pressure is the correct spot there. Okay, now related to dirt separation. So let's say in the past we've used Y strainers. Y strainers are great at getting something like a marble that a kid put into the piping out and holding it in a specific spot to be blown down. We suspect a lot of Y strainers are not blown down, that nobody remembers that that's actually something they need to service. The problem with a Y strainer is anything smaller than the mesh is just going to keep getting pushed through it. So the difference between a Y strainer is you're going to catch big stuff with a Y strainer, welding slag, big pieces of sand, big chunks of rust, a welding glove. We got back in like an 8-inch separator one time. They said it wasn't flowing very well. We opened it up and there was just a leather welding glove inside of it. It's going to catch that stuff. But little magnetite and pieces of rust and pieces of sand are just going to go right through that mesh all the time. You can get a smaller mesh, but it's just going to plug faster. So the difference with a dirt separator is it's a collision media, that same collision media that we talked about before, where the debris is going to hit and fall down to the bottom. The bell of a dirt separator is really important. You can take some cost out of those devices and make them smaller, but you want a low velocity zone here so stuff hits and falls down to the bottom. So now if I had 10 GPM and we've got two cups of dirt at the bottom of this thing, it doesn't affect the pressure drop going through that device. So even as you turn up the flow rate through these devices, you can see that the pressure drop across the separator is very different from a plugged Y strainer that's going to add a ton of pressure drop across, in this example, 12 GPM, 70% plugged. We're adding a 5 PSI, or let's see, we're adding like a 4 psi drop across that device. That's going to take you out of your design considerations for what pump size you needed in that case. We don't want that. We don't want to start to choke the boiler for the flow rate that it's looking for, as an example. Okay, the last piece is magnetic separation. This is a newer thing that in older buildings, and I think that like in the GTA, there are going to be a lot of old buildings that maybe had cast iron boilers a long time ago, 100-year-old building. There's a lot of steel piping, cast iron radiators or something like that potential. So you've got a lot of metallic magnetic debris blowing around in that system. And an old cast iron boiler with a permanent pump wasn't really a big deal. It just kind of churned through, or it would settle to the bottom of the boiler heat exchanger, but they were big cast iron sections and it wasn't a big deal. Now we've got this great new technology with modulating condensing boilers and ECM circulators. The problem is we have a lot less margin for error there. We've got smaller passages through a heat pump or a modulating condensing boiler. This magnetite can cook to the inside of the heat exchanger, or it can get stuck on another magnet. So ECM pumps have a big magnetic component that is going to attract this magnetite, and it's going to get stuck to the rotor. This is actually from our building in Caleffi in Milwaukee, that this was an ECM circulator that failed on us, and we were wondering what happened. We opened it up. This is at the time like a 5-year-old building, but there was some steel piping and there was an error issue because we had a leak that we took some time to track down, even in our own building. And what happened is it created some magnetite from the continued rust from the inside out of the system that all accumulated right on our ECM pump and caused it to fail. So we definitely don't want to be replacing commercial ECM pumps in the buildings that we design and install and service. So just having a bigger magnet upstream of that is what we're going to do to prevent the magnetite from getting stuck in the really expensive stuff like the commercial ECM circulators or cooking to the inside of a boiler heat exchanger, as an example. How do we know if we need more magnetic separation or if we need to blow down these devices more frequently? You just kind of have to test. So what I would recommend in a commercial system is to get a big white bucket and blow the vessel down into the bucket and see how much of this debris is reactive to a magnet. And then just put that into the schedule that the maintenance person should do that once a week in the most extreme cases. And if after a week in one of these separators, you only get just a little, couple grams of debris, then maybe you only have to do it once every 6 months or once every year when you're doing an annual service or something. The test, there's no specific rule there. In a system like this with old cast iron radiators, you're just going to do that forever. You're going to have some sort of air that's going to enter the system in the building, and you're going to have to do that forever. You're always going to be kind of rusting from the inside out. Or if there's a leak and you're introducing fresh oxygenated water through an autofill valve or something like that, the game keeps going on and on and on, and you have to catch that magnetite and keep up with it over the years. Okay, I'm going to just go through a couple slides at the end here to kind of show the different sizes of these devices. So air vents and air separators can go from 1/8 inch to 12 inch in Canada for CRN listings if that's required, and then 14 inch for the bigger separators down in the States. Same thing here, 3/4 to 12 inch for the Canadian devices. In the bigger dirt separators, the flange versions, there's still a dry well magnet down here, so you don't have to get your hands dirty with the magnetite or anything like that. You just pull that out, blow this down into a bucket, and you don't have to touch or disassemble the components at all. In the biggest versions, it's actually 3 different stacks of magnets that go up into the vessel to grab the magnetite with higher flow rates. This one I see quite a bit in pictures that people think, oh, I can get an air and dirt combo separator and it's going to save some money. The problem is air and dirt combo separators are really for chiller applications, because this point in a chilled water system, the hottest water where we can separate the air and the dirtiest water coming back from the return are in the same spot. In a heating system, they're in opposite spots. So the dirtiest water is on the return, the hottest water is on the supply. In a chiller system, this is a great device to use because they're in the same spot. In a heating system, if you use a combo air and dirt separator, you're sacrificing the performance of the air or the dirt a little bit. You don't want to catch the dirt after it's gone through the chiller, and you don't want to separate air on the cold return. It's not going to be as effective. So what I would suggest instead is separating them and just getting an air and dirt separator for a heating system and having those in the proper place for best performance. But if you're doing big chilled water systems, this is a good way to go as well. And then we'll wrap up with just a couple pictures. This is one from Ontario. So this is with PPR. It could be copper, it could be PEX, could be anything, steel piping. Depends on the flow rate with this ECM circulator going out to the building, coming back to the hydro separator with the flange connections here. We're in good shape to keep these two wheels separate. The ECM pump could be any number of GPM. We've got 3 different boilers that could come to life on this side, and they're not influencing each other. 1 boiler or 3 boilers could be on if you've got enough of the header right here, and this is size for all 3 of those flow rates combined. We're not going to have any issues, choking flow to any of these 3 boilers as they come on. And you could put a flow meter right here and see that there's 0 GPM flow on that screen of that pump. As an example, maybe even when these boilers are calling, that's properly separated. This is another example. 3 big commercial boilers, like 1.5 million BTU boilers with the hydro separator above here. If you were going to do closely spaced tees at this size, you're going to have to spend a week welding that, and you would need 3 times the amount of space, which could be a drag in a mechanical room like this. So this kind of nicely tucked up into the vertical space next to the boiler there, and is a good example of a commercial separator in this scenario. Another example here, a lot of different ECM circulators going out to the building. I think this was a geo system, and we've got all the flow meters coming back here. So in this case, you would be able to just pull the pin of this flow meter, this quick setter valve, and see what the flow rate was and verify that that's matching the circulator, and also that you're properly separated there. You shouldn't see any GPM on any of these flow meters if this boiler is on and these circulators are off over here. Okay, that takes me to the end of my slides. If there are other questions or any other comments, jump in here and I'm happy to answer them, and then we can wrap up right at the 20-minute mark.
Perfect. Yeah, feel free, guys. We have like 5 minutes left still. So if you have any questions, any comments as well to anything that you guys have seen out in the field as well, to anything you guys want to kind of bring to light or maybe pick Max's brain at, please feel free.
Sure. Yeah, and all of this to say, there's no perfect answer for what hydro separator to choose. If I were a designer, one day I might go with closely spaced tees. Most days I personally would go with a hydro separator, and in some cases I would use a buffer tank. So there's not like a right or wrong answer here. When applied properly, all of them will absolutely work and can be part of your toolbox as designers to figure out what works, or as installers to figure out the best use of your labor hour to get the project accomplished and make sure that the system is going to work efficiently.
Mm-hmm. All right, we'll give it a couple more. We'll see if, okay. All right, well, we had Tasha that said great presentation. Thanks for lots of great information. So thank you for that, Tasha. All right, well, I guess if we don't have any questions, I guess I can kind of just, we'll do a little bit of a summary. Again, Max, thank you so much for presenting. Again, you could see also, too, Max has his email right there on the screen. If you guys have any questions as well, too, obviously, you can shoot him an email. But also, we kind of just want to wrap up and say thank you very much for everybody who, also quickly before I do that, someone asked, do you guys have an Ontario rep? And if so, who is it?
A quick go.
Okay.
In Ontario. Yep.
Perfect. All right. Well, if there's not any more questions, guys, thank you so much for participating in our Hydronics Technical Training Day. We really enjoy that everybody kind of made it out here, was able to sit in, spend an afternoon with us, and kind of learn a little bit more about hydronics. And hopefully you guys took something away from it. Of course, we also will be posting a supplement in our March-April issue of the magazine, which will kind of cover all the sessions that were covered today and also a little bit more as well, too. So please stay tuned for that. And of course, we will also have our next technical training day, which is going to be on April 10th, and it's going to be on plumbing. So feel free to sign up for that as well, too. And again, guys, thank you so much for joining. Thank you, Max, and all of our other amazing speakers for taking the time. And we really hope to see you guys at the next one. Thank you, guys.
Thank you, everybody.